Okay, just to start off this class, at the end of the last class we were discussing divergences in open string theory, and we realized that the bosonic open string did have UV divergences, but that lied for, but in a different way from the closed string. These UV divergences were interpretable as IR effects in the closed string set. Now, there was some unhappiness about this interpretation, especially from pure theory. So let's just spend 5 to 10 more minutes on it, just to clear up all the unhappinesses. You see, before looking at the physical interpretation, let's look at it technically. Okay, what did we have? We had this strip partition function, which we then integrated over modular space. That was the thing that we obtained. Okay. Now, we were interested the troublesome divergences. The troublesome divergences happened in the limit of very high temperature, from this point of view, because the UV. Very high temperature means very small beta, so very small size of the strip. So this thing we call T, so very small T. Is this clear? So it was obtained from a world sheet of this form, but this side is much longer than this. Okay, now this is the regime in which in quantum field theory it's very difficult to directly calculate a partition function, because it's a regime in which many different states contribute to the partition. Okay, so the direct calculation which we have in the exact thing, we could analyze that mathematically, and we did, using modular invariance. But actually, our analysis of it mathematically has a just before we integrate over space, just as function of t, has a physical counterpart. See, what we did in order to analyze this was use a modular transformation of this partition function. So that was purely mathematical analysis. Okay, but in the end, we got the answer in terms of S, which was 1 by t. Now, you see, because we're dealing in a conformal field here, every partition function that we calculate is invariant under uniform rescalings. So this object here is the same thing as, let's take this side and rescale it to be of size 2 pi. Okay? And then, okay, so let's first draw it this way. So this is the same thing as just at the level of worldsheet conformal. Okay, this is a circle. This is a circle of size 2 pi. And this is a strip of length 1 over t, or 2 pi, 4 pi squared, something like that. Won't worry about that. Okay, so this is okay, where at these edges we put particular boundary conditions on the string. Is this clear? So we got some boundary condition here. Some boundary condition here, and we go push. Okay, now so we're calculating a path integral with these boundary conditions. Now, if we calculate this path integral, okay, we cut the path integral here. What we're going to get is some state of the closed string. Okay, what exactly happens at the edge? We'll worry about in a moment. But anywhere apart from the edge, it's going to be the path integral of a closed string on a cylinder. So we get some state of the closed string. Okay? So clearly what's happening is that the boundary conditions are preparing some state, whatever it is. And this state is propagating to the other boundary, where that same state is again hiding. Okay? So this is schematically, let's call this state whatever it is, B. And this B prime, but it's the same boundary condition, so let's call it also B. Is schematically e to the power 1 by t times time times Hamilton, okay, yeah. Times the Hamiltonian closed string times speech. Just as a mathematical level, the path integral that calculated the open string partition function can also be represented, okay, as a particular closed string state created, propagated over time t, and annihilated by the second closed string. What this state is, that's a maybe enough course to describe. This by the way is called the boundary state. The state B is called the boundary state. It's the closed string representation of open string boundary conditions. Okay? And it's a much studied object, and there's a lot to say about it. But it's not our purpose at this point to discuss the boundary state. Again, we can worry about, it's actually not difficult to give an explicit oscillator representation of the state and so on. For open string boundary conditions, it's a nice and interesting subject, which we'll probably return to.
Does this boundary condition violate the local symmetries?
Does the boundary conditions violate? Yeah. So these this state is not invariant under all the Virasura generators. That's what you're asking. Yeah. Okay, but it is invariant under half of them. Right. Effectively, for the same reason that the open string boundary conditions were broken. Half of them. Yeah. So it's the same. Symmetry analysis is the same. But it doesn't matter. You see, any state in any quantum field theory, the vacuum, most quantum field theories, vacuum is the most symmetric state in the problem. Look at any other state, it will not be invariant under all the symmetries of the theory. That's not an unusual situation. It's not a bad thing for a state to be invariant under pure symmetry theory. Most states are. Okay?
Why don't we then do like open string? Why don't we then, instead of looking at scattering matrices only for open strings, why don't we deal with general? Instead of dealing with S matrices, where we are only looking at asymptotic states for open strings, why don't we, impose such a boundary condition and look at scattering matrices as fine?
You see, we mustn't confuse the world sheet with space-time. Everything we're talking about here is world sheet. Okay? So, we're looking at a partition function with finite distance on the world sheet. We did this even for the closed string. We computed the partition function of the closed string at finite tau. For the same reason that you didn't complain there, you shouldn't complain here. This is a purely auxiliary world sheet calculation. Okay? We're not saying this computing scattering of states from one localized point in space-time to another. We're not doing that. Yeah. We can never do that in string theory. At least when closed strings come. In some limit where open strings decouple from closed strings, then in that sense we can. But we don't know how to do that in string theory in any sense whenever closed strings couple to open strings. Okay? But that's not what we're doing. We're just taking the partition function of the world sheet and analyzing it in a purely, just looking at that path integral and giving it another interpretation. Same path integral. Is this clear? Okay? Now, because this is the transition amplitude from one state to another state. Okay? Because it's transition amplitude from one state to another state, we can insert a complete set of states in the middle. It's convenient to insert a complete set of eigenstates because then the eigenstates will propagate freely. Okay? So, suppose we insert a complete set of closed string eigenstates, let's call them M, we get dm times mv, okay, times e to the power minus em by t, or let's call that ems, where ems are the closed string states that propagate the string. Okay, so as long as we are interested purely in the analysis of the conformal field theory, just the worldsheet partition function, there must be some numbers for which this is true. So if we are interested in the limit of very large S, this is a useful representation because there are the lowest energy states that have non-zero overlap. We'll know. You see, at some point last time the question came up, why did we get the number 24 if you remember, massless states? It's because only 24 of these states are non-zero. That's this. Though we're not getting into that in detail now. That's an interesting but large subject. So the standard boundary states. Okay? Now, you see, so what was the key point? The key point was that in our purely mathematical analysis, we had dt by some blah blah blah, which turned into just simple ds times exponentials. Okay? So that told us that positive exponentials are constants for problems. Right? Because we were looking at the limit of large x, yeah? So positive exponentials are constants for problems, negative exponentials were not. Okay. So firstly, just purely from the, just in conformal field theory, when you get a positive exponential, you get a positive exponential if you have a closed string tachyon. Okay? So positive exponentials, which are a problem, are an artifact of having a closed string tachyon, and so will never bother us. Okay? Now, then there's the next question. What about the constants? Okay? Now the constants are there provided you have the closed string master states. Okay? And that will always be there. Okay? So this tells us firstly the nature of the problem of UV divergences. The nature of the problem of UV divergences, okay? The nature of the problem of UV divergences is that well, it will arise whenever you have a closed string tachyon, or will arise whenever you have closed string massless states, provided these states couple to this boundary state. Okay? Now we are going to deal eventually with string theories that have no tachyon. So we are not going to do the analysis with the tachyon. Okay? The tachyon is problematic for many reasons. Let's forget about it. But of course we're going to deal with closed string theories that do have massless states. Okay? So the massless states you can't dispose of. So what's the other alternative? The other alternative is that the massless states don't couple to our boundary state. That the full state of the theory, whatever it is, okay, does not source the graviton. Okay, or the dilaton. Now, this sourcing is what? You see, from the closed string point of view, any diagram involving open strings can also be thought of from this closed string point of view. Okay, so if you have some vertex operators inserted here, that would change this boundary state. That's clear, right? Something else going on. Okay, so from the closed string point of view, this diagram, this thing represents the amplitude for a closed string to be created by its boundary state. Let's look at that statement diagrammatically. You see, what is it? It's the amplitude. You see, it was the amplitude that in this boundary state you find a particular closed string. When you propagate this boundary state, you find a particular closed string. Right? So that is the same thing as this diagram. You take this boundary state, this particular disk, and you propagate it away to, instead of this boundary state, to that particular closed string of interest. Okay? Now, since that closed string of interest is an eigenstate that can live on a cylinder of any length. So let's take the length of that cylinder to be infinite with the closed string disk. But now make a conformal transformation. Get this tube down to the disk. So this is the same thing as this operator. Okay? This object is the same thing as the one-point function of the vertex operator corresponding to that state n inserted on the disk. Okay? So we've concluded that we're going to have this problem whenever we have non-zero one-point functions of massless closed string states inserted on the disk. These one-point functions are called poles. Okay? And so far, everything that I've said is just purely mathematical analysis of conformity. Okay, I've not mentioned space-time so far. Okay, so clear, just purely at the mathematical level, we say that in order to have consistent open string theory, namely open string diagrams with no UV divergences, we want to cancel all closed string massless diagrams. We want to deal with a theory which has no massless closed string diagrams. I say cancel. Okay, I say cancel because, as you will see as we go on, there are some ambiguous, there are elements, things you can add to your background. And you can choose combinations of them that are added up so that the tadpole is cancelled.
But I don't understand here. So all you're saying is, we can write this this open string partition function in such a way that we have this combination where there is an overlap between the closed string states and the boundary states.
Yeah.
And you're claiming that the constant for the massless case, the constant part which gives rise to one of the divergences, that will be 0 because of this absence of tadpoles. Is that?
I'm saying that if we could find the string theory where that is 0, okay?
Okay,
then we will not have the problem of UV divergence.
Then that 24 term will also not appear.
Will not appear? Yeah. Okay? It will not appear. The mathematical level of what we would say is that there's no divergences. But I'm giving you an alternate way of characterizing that. The alternate characterization is that if you find a theory where the disk, there are no tadpoles at order 1 by g in the disk or any other diagram that contributes in the same order. Maybe I should discuss orientifolds originally, but there'll be orientifold diagrams. Orientifolds will cancel equations. That's the answer to your question. But my plan was to first complete the discussion of open strings and go back to orientifolds. Maybe I should have, not done it in that order. But anyway, okay. So if we can find a background in which these tadpoles are 0, then we know we will not have problems with UV divergence in the ocean. It's the only statement that's we need. This statement is non-trivial because we will deal with backgrounds with 0 tadpole. So then we will not bother at that point to check whether the open string 1 loop divergence vanishes or not, because we guarantee that it will be. Is this clear? Now, in the last part of last time's lecture, I tried to say this more physically from the point of view of space-time. So far, everything we've done is just mathematics, and it's hard to argue. You can't argue with mathematics, so it's correct. Okay? Now I'm going to give you a physical interpretation from the point of view of space-time. So you can separate these two things in your mind. Okay? The physical interpretation went as follows. You see, what is a tadpole? What is this diagram? This tadpole diagram. It represents a 1-point function of some state. Okay? So in a Lagrangian, we know that the states that we're dealing with have some kind of data. So suppose you had pretend they're scalars. Nothing changed. Nothing essentially changes. Okay? So suppose you had some action which had d mu phi both x squared plus m squared phi squared. If you have a 1-point function, it's at disk level, so that's a factor of g. Okay, so coupling constant. So you have some g times phi. Okay, now we have to understand two things. We have to understand the point. You see, it was not a problem if we had tadpoles for massive states, because they appeared with a negative exponential here and they never gave rise to that. Okay, so we have to understand two things. We have to understand why tadpoles are bad for massless states, but they're okay for massive states. Okay, this is going to be now physical interpretation. So the physical interpretation runs as follows. Look at this space-time Lagrange. Okay, now this was 0 dollar term, quantum effect, some coupling constant effects, gives you a small additional term, g times phi. What was the vacuum of this theory? Just guess again. Vacuum of this theory was phi equals 0. What is the vacuum of this theory? It's phi is equal to whatever, minus g by 2m squared. Everywhere in space. You get by completing the square. It's not phi is equal to 0, it's phi is equal to some shifted value. But who cares? It's a small difference, small shifted value. Is this clear? Because g is a small number. The original potential of our theory was like this. Now you've added a linear term to that. So depending on the sign, the linear term shifts in some direction, so it's like that. But this is very different. It's not very different from that. Okay, brace phi goes to minus phi squared. But it's not a drastic change. It's got the new vacuum is in some sense close to the old vacuum. Okay? So you can deal with the effects of this term in perturbation. So small change on the old situation. Is this clear? Now, let's, on the other hand, mathematically, how will you analyze this? You will analyze this by saying, well, firstly, we should probably be more careful if we wanted. It's minus A over that.
Minus of the overall.
Minus of the overall thing. Okay, whatever. Yeah, that's a minus of the overall. Okay. So mathematically, what we would have said is, let's say we're searching for translation invariant vacuum. Now we solve the equation of motion. The equation of motion times square phi with a 2 plus g is equal to 0. Okay, and then we solve that. We'll get phi is equal to whatever it is. Now, on the other hand, suppose we set m equals 0. Suddenly we see that the equation has no solutions. Has no solutions because the equation is that just g is equal to 0, which is not true. Okay? So that tells us that there are no translationally invariant solutions of this theory with a dipole if the field is massless. It's not true that there are no solutions at all. Because there are solutions. But the solutions will have to balance off this del squared phi against constant. We think del squared is equal to a constant. One way to solve it is, for instance, phi to be a linear function of the coordinate. And that sometimes happens in more complicated. But this is a big change in the theory. Okay? For instance, even if your vacuum here is not very much changed, you go far enough away, it's changed very much. Okay? Which tells you that if you try to do perturbation theory, you will have problems at long distances. Because there's no sense in which the change in your theory can be thought of as small everywhere. Over a local patch, it doesn't change very much. And because phi is changing linearly with x. But the slope is very small, so you can ignore it over a local patch. When that patch becomes about 1 over g, you can't ignore it anymore, you're going to run into trouble. Perturbation theory always breaks down if you assume that you've started that, when does perturbation theory break down? If the theory is well defined. It breaks down for a number of reasons, the most common of which is that your starting point is not near the right solution. If you do perturbation theory thinking, well, let's do perturbation in G, but you start with a solution that's far away from the right thing, that won't work. And that's what you're doing. Is this clear? This is the philosophy of the spacetime. Now, what is the mathematics of the spacetime? The mathematics of the spacetime thing, which is almost trivial, but anyways worth seeing, is the following. Suppose you want to calculate a one-loop graph in spacetime. This vacuum, not one loop, sorry, the vacuum energy graph in spacetime. There's a diagram that goes like this, with 2 copies of insertions of this and 1 propagator. You see, the answer to this diagram is the inverse of the propagator. Okay, by translational invariance, the only momentum that goes in here is 0. Since the inverse of the propagator at momentum equals 0. Okay, what is the momentum flowing through? It's 0. Which is fine if the particle is massive. 1 over m squared. But is infinite if the particle is massless. Okay? So you see immediately that in this trivial quadratic theory, if you try to compute the vacuum energy, you would have a graph that would give you infinity. Okay? It's coming from this particle propagating over very long distances. Well, all distances. Okay. It's some graph that gives you just infinity. And it's symptom of trying to do perturbation theory about the wrong background. Actually, typically speaking, perturbation theory breaks down for 2 reasons. Firstly, if you're doing it around the wrong background. Or secondly, if you're asking the wrong question. Typically, these are 2 typical reasons. And in this case, we just did perturbation theory with the wrong background. It's not true that this theory makes no sense. There is some background, some translation non-invariant background, around which if you did perturbation theory, everything would be fine. Okay? But that's not what we're doing in string theory. We're taking this closed string to propagate about the space. And then when you do perturbation theory, you get the analog of this problem.
What did you actually mean when you said asking the wrong question?
What did I actually mean? I have in mind infrared divergences and gauge theories. You should be doing some inclusive kind of calculation. Okay. Okay. Now, the last thing that I said last time, okay, which again we should keep in mind, is the following. Suppose what I want to do is to diagnose that this problem is exactly the analog of this problem in space time. They look similar, but how do I know they're really exactly the same? So one way to do that is to change this question a little. If you somehow manage to inject some momentum into this vertex here, you somehow manage to do that. You make this tadpole not translationally invariant. That's how you do it. If this thing here had some momentum, this g was a function of x, and had some momentum in it, then this vertex would break translation invariance. Right, then g a function of space-time. Okay? And then we look at the differentiate with respect to g of k. Suppose that has a function of space-time supported at some value of k. Okay, so replace g by g times e to the power I kx plus complex conjugate perhaps. Okay? Then the same diagram, everything would go through in Feynman diagrammatics except this vertex operator would, momentum conservation would say that there's a jump in momentum between here and here. Here there's no momentum. Here there must be momentum k. And therefore we would get 1 over k squared in this thing. Is this clear? There would no longer be a divergence. It would be some finite answer. It's hard to compare infinity with infinity. It's easy to compare finite numbers. So that's the motivation. Is this clear? So what we want to do is to check whether in string theory we do get this 1 over k squared if we change the closed string source to have some space-time momentum. Okay? Is this clear? Now, what was the closed string source? The closed string source was the boundary statement. How do we change this closed string source to have some space-time momentum? Well, we put some vertex operator on the disk and give it an e to the power kx dependence. Clearly, that's now a source that has a specific momentum k. Okay? Therefore, what the question we're asking is that if we do the same calculation, now not with a vacuum, but with some disk, some insertions on the disk, whose net momentum is k. The details of the insertions shouldn't matter. As long as the net momentum is k, the leading divergence here should get smoothed out to a 1 by k squared. That would be a test of whether our interpretation of the divergence in open string theory was correct. A closed string interpretation with space-time. The mathematics, the first part of what I said, is unaffected by this, but just the physical interpretation from the point of view of space-time. Okay? So, last time I outlined to you that this does happen. The basic point was that when you put some vertex operator here, in addition to the, you need to contract these vertex operators. That gives you z12 to the power k squared. z12, because this side is so much smaller than this length, to lowest order, the large s limit, is essentially e to the power s. So you get an additional e to the power minus s times k squared. So the term that was a constant here that represented the propagation of mass force becomes a negative exponential. The coefficient of that exponential is k squared. So when we do the integral over all s, we get 1 over k squared. Okay? We do the integral 0 to infinity e to the power minus k squared s, and the answer is 1 by k squared.
So in this case, we actually had an equation which is telling us that there's no, that we are doing something wrong.
In which case?
In the case of this field theory.
Yes.
So what would be a corresponding equation in that case? Say like we should take it that we are not.
You see, the corresponding equation. Yeah. The divergence is one symptom of this.
Now, how would I know which equation should I solve to get the correct answer?
Which equation should I solve?
If I with getting translation non-invariant.
Okay, very good question. You see, what was the condition that we had initially? Okay, that we actually had a good background of string theory. Well, I mean, why did 26 dimensions work while 25 don't? The condition was conformal invariance with C equals A. And of course, flat space string theory with boundary conditions is conformally invariant with C equals A. Now, you see, that was the condition for having a valid classical solution of string. That condition, the condition of conformal invariance, is modified when you take into account loop effects. Okay? Which is basically the statement in field theory that if you've got some vacuum of a classical action, that may not be the correct vacuum of the quantum action. Okay? The way this happens is what's called the Fischler-Susskind mechanism. Okay? Where you see there are two sources of divergences now. There's divergences when there are two kinds of divergences. One that happen when vertex operators hit small loops in the integrate. There's new divergences of a certain sort. Okay, again we'll get to this. But there are new divergences of a certain sort in the integration of a moduli space, which can be absorbed into world sheet, which becomes sort of effectively local on the world sheet, and can be absorbed into world sheet divergences. So then the correct condition, when you look at string theory as you go order by order in perturbation in the coupling constant expansion, okay, is to solve some equations that at lowest order are the conditions for conformal invariance of the world sheet theory, but at higher order the string coupling, okay, are some deformed equations that are not quite the condition of conformal invariance. Now, the question is whether these deformed equations have a solution. Those deformed equations are the analog of this.
Okay, in this particular case, what is the field which will become which will develop, I don't know whether the question makes sense, which will develop
oh, you're asking what is the, what is it? It's the one thing that many things could. But one thing that the dilettante is one such field. Okay? Yes, so the final answer to string theory on this background would be one particular solution. Okay? I'm not sure it's unique, it's probably not. But one particular solution is a linear dilettante. Okay? That's a known exact theory that would do the job. Okay? With a linear dilettante. Okay, so that was your question, that was easier. Okay, we postpone the discussion. Fischler-Susskind kind of stuff. Okay, good. Other questions or comments? We're spending time on it, I know, but it's important because these are, the important conceptual issues of perturbative string. Other questions or comments about it? If you have any questions or comments,
okay, say if it is there some way of saying that this particular state is actually sourcing it, and we are not following. In this case, there is we can, if we wanted, we can physically interpret these equations that G is something like a source, and you're not following the equations.
right?
Okay, there's a source and there's a quantum. By quantum mechanics, there's an effective source.
Right. Yeah.
And you're not following it correctly if you're just saying phi is translation in
Exactly.
So here, is there some way of understanding that this is actually sourcing the mass?
Yeah, you see, that's the tadpole diagram. When do you know that you have a source? See, if you're about a true solution to the equations of motion, they're all one-point functions. A zero. So if you've got a one-point function in your theory, you've not solved the equation. Okay? So that's this. This calculates one-point functions. Now, though that's too slick, because it does not differentiate between whether these one-point functions can be removed by small changes of the vacuum or not. You see, you would have a one-point function whether or not there was a mass here. But if the mass was something finite, then though the one-point function existed, you were working around the right pattern, the correct background was not following. Okay?
In fact, the massive tadpoles here would shift.
Would just shift the negative exponentials a little bit. Who cares? Okay. So when you if all closed string backgrounds would be turned down a little bit, but a small amount. The amount about the G doesn't make any difference here. But it's a maskless guy that is not getting turned down a small amount. It's totally changing the vacuum. Okay? So this 1 point function is a symptom that you've not solved the classical equations correctly. That's always true. But there's a more subtle question that you have to ask. So the question is, granted that you haven't solved the classical equations exactly, can you change your solution a little bit to solve it? When you can, perturbation theory still works. When you can't, it doesn't. Is this clear?
There's just one more question.
Please.
Okay, so here the conclusion, if I understand it right, is that there's an infrared problem in the
Closed string set.
Yes, sir. It shows up as an ultraviolet problem in the open string set.
That's exactly right.
But why? I mean, let's say if I'm not doing it right in the infrared, in the closed string, I mean, why would it show up in the ultraviolet or open string?
That's a very good question. You see, technically we understand it. Technically it's the statement that the ultraviolet of the open string theory is governed by T being very small, which is exactly the statement, the same mathematical statement as S being very much.
But technically it goes through the worldsheet modular invariance, what is the space-time?
Yeah, that's a very good question. You see, this I don't know if there's anything particularly good to say about this. Or if there is, I don't know what it is. It is it's basically in the end a deep property of string theory that every open string calculation can also be interpreted in another channel. The same calculation can be thought of in two different ways, both of which are completely correct. Think of it in one way, summing over very high energy states of open strings. You think of it in another way, summing over long distance closed strings. And these are both identical things. So it tells you that somehow, there's some sort of mixing between ultraviolet and infrared in string theory, seen in some particular way. Okay, but I don't have what do you like to see? Well, maybe I should say the following. Maybe what? The point somehow is that you can ask what configuration of open strings going around in this loop is a closed string propagating over very large distances. And that configuration is very high energy open strings. Okay, basically I just don't know what to say. From the point of view, worldsheet is very clear. From the point of view of space-time, I don't know what to say. I'm not sure anyone does. Basically, because it's very unfamiliar physics from the point of view of field theory. It's no field theory anymore.
Okay, so I just wanted that question to be answered. Let's say so here there is, is there a way of understanding it? Okay, this is just a question. Is there a way of understanding it if I just kept the, just say, some states here, some low-level states here, some
No, absolutely not. You see, because the whole, in order to build up the maskless closed string, you need all of the infinite turnover of the open strings. So absolutely not. You see, because we're going to this limit, t small, where you see the maskless closed string. You're going to the limit of t small, which is s, at the limit of t small, all states in open string theory contribute equally. So in that limit when you build up this closed string. Okay, so absolutely not. if you just truncated this to level 20, there's no sense in which you would see. There's no sense in which you would see propagating. Okay? Except this the fact that you can view things in different channels on the worldsheet, it's called the worldsheet duality. And it's a very important property for perturbative string. Okay? Which, as we have seen, has very sad consequences. Okay, good. Other questions about it? Fine. Okay, so if everyone's happy with all of this, now then let's move on to the study. Okay, now we're moving on to chapter. So we finished our discussion of chapter 7, apart from the discussion of orientals, which in my plan I'm going to get to right at the end of this month, just before we have your exam. I want to discuss open string theories first, then ramifications, and then orientals last. So from the point of view of tadpole cancellation, we should do that. But anyway, let's stick to this plan for now. So the last thing that we want to do in our discussion of open string theories is chapter 8, okay, of Polchinski, is toroidal compactification of string. Okay? So though one of the reasons I'm discussing toroidal compactifications is that it will lead us to new phenomena involving open strings. They may lead us to understanding deep rings. The discussion of toroidal compactification starts in the absence of open strings. You don't need to have open strings to discuss toroidal compactifications of any theory of gravity, string theory. So let's start by discussing toroidal compactifications without open strings. We'll add them in at the next stage. Okay? So the theory we want to discuss is the theory in which we've got x0 and then xi, I is equal to 1 to 24, and then xd, that's x25. And we break the Lorentz symmetry of the theory by choosing one of the coordinates. At a later point, we will generalize this to having more. We start with just one, namely x25, and make it bigger. Okay? So we want to, our goal is to study string theory in this manner. Okay. Now, maybe one quick statement about what this means before beginning a systematic study. As you've seen, x25 is a field, whereas R is a number. Okay? So what this means is that the zero mode of x25 is periodic, whereas all the oscillator modes of the theory are unaffected. Okay? So this periodicity is a statement about the periodicity of the zero mode of the theory. For instance, suppose I took the theory on a circle of length 2 pi, as we'll be doing, and Fourier expanded it. The periodicity, the statement is that the constant piece is not a single valued field in space-time. Okay? Whereas the oscillators are just totally unaffected by this. Okay, this is always something to keep in mind. The toroidal compactification, what it does from the point of view of string theory, is change the zero mode sector, leaving everything else unaffected. Okay, so we will soon be studying string theory with this thing compact. But before doing that, we should start. I wasn't sure you guys were all completely familiar with this. I wanted to quickly review how just the theory of low energy gravity, okay, coupled with the scalar fields and a B mu nu field, okay, would react to toroidal compactification.
Here R is somewhat large enough, like
it's any number. When we study string theory, it will be any number.
like how does it compare with the first massive field?
It's arbitrary. Okay, at this point, it's arbitrary. It could be made equal to that, could be made smaller than that, could be made larger. Okay, we'll say that at the level of classical string theory, this is a solution to the equation of motion from order. So it's just a number and that's in ions. Okay, but there'll be many things to say about this as we go on. Okay, but to start with, imagine that R is big. Okay, and we forget about the tachyon because it won't be that superstring. So that the effective spacetime action in the space will just be the massless modes of the theory, okay, on the circle. Okay, so what we're going to discuss is the physics of what's called Kaluza time reduction. Okay, you have some familiarity with this, I'm sure, but anyway, let's discuss it in as thorough fashion as we can, because it's important to understand what effects further just from field theory before we look at the new effects. Okay, so what is the action we're discussing? So consider a theory with okay, so I'll follow Polchinski's conventions and use the symbols Mn to denote indices that run over all 26 dimensions, whereas the symbols mu will be used to denote indices that run over the non-compact dimensions. Okay? Now, the first question I should ask is, okay, now, we are going to deal with, let us try to start with, to deal with configurations of the system, okay, which have no dependence on the 25th dimension. Okay, so suppose we are interested in energy scales that are large compared to, distance scales that are large, or energy scales that are small compared to, distance scale is large compared to r, or energy scale is large small compared to 1. Okay? Then, as you're familiar with, you shouldn't excite the wave functions have no dependence on the top direction. So let's try to understand, how that works. Okay. So the first thing we're going to do is to parameterize the metric of this higher dimension space in a way that will be convenient from the point of view of the low dimension. Okay? So suppose we take the metric, which is ds squared, and write it as gmn dxn, that's just the definition. But we say that this thing is the same as g mu nu dx nu plus e to the power 2 sigma dx ds. Instead of writing 25, I write d to be consistent with Polchinski, plus a mu dx. Maybe Polchinski minus, no, plus, okay. Which is good. Well, how this way. Okay. So, I've not done anything here. I've just taken an arbitrary metric and written it in terms of new variables. Okay. Now remember that we will be dealing with configurations that have no dependence on the xd direction, but can be arbitrary functions of the x mu direction. So the first question you should ask in such a situation is what happens to the symmetries of the thing. The symmetries of the original thing, the coordinate invariances of the original theory, which of those survive? So there are two things that survive. The first one is the obvious one. Coordinate redefinition of the 25 non-compact dimensions in terms of the other 25, in terms of themselves. You may wonder, what about a redefinition of the 25 dimensions in, say, x mu as a function of x mu and xd? But that breaks our postulate that nothing is going to depend on xd. Because a field that was x mu dependent will now become xd dependent. Right? We don't want to deal with such configurations. Okay? So within the restrictions that we're laying out for ourselves, that we will deal with fields that don't depend on xd at all, that coordinate invariance is no longer there. However, there is something else. And that is, we can take xd and redefine that field, that coordinate, in an x mu dependent fashion. Suppose we did xd is equal to xd prime, or xd prime is equal to xd plus lambda x. I kept this linear with coefficient 1 because I don't want to change the fact that xd is a periodic coordinate with periodicity 2. Okay? What's this doing? It's just, we've got this coordinate here, and it's saying that there is no preferred way to set the 0 of xd on the circle. I could choose that 0 to be anywhere I wanted, and I could choose that anywhere I wanted. in an XMU dependent fashion. No, this is a function of XMU, not XMU.
XMU,
Yeah. Okay, so there's no restriction to the function. Is this fair? This is a fine reparameterization concept. Now, under this reparameterization, various things will change. Okay? Let's see what happens here. You see, the metric will change as a metric does under coordinate transformations. Okay? But there's a very easy way to see how things change. You see, after we make our change of metric, change of coordinates and change of the metric, the line element remains invariant. What change in this new parameterization will leave the line element invariant? Well, so g mu will go to some new function g mu prime, but that's not changing, right? Because dx mu dx mu is not changing its coordinate. Okay? E to the power 2 sigma will go to some new function e to the power 2 sigma prime, but that's not changing because the dx squared term, which is here, is not changing. Okay. But a mu will go to some new function a mu prime, and that is changing because dxd goes to dxd plus del mu of lambda times dx mu. So we can absorb that shift into a shift of a mu, which is a mu prime is equal to a mu minus del mu lambda. Okay? So what's the statement? The obvious statement looking at it in this form is the following. Suppose you made this coordinate change, you calculated the new metric under this coordinate change, rewrote it in this form. You will find these fields remain invariant, but this one changes. And this one changes exactly like the U1 gauge field changes under the gauge transformation. Okay? So we see something very interesting. When we look at gravity on a circle, okay, we have an effective gauge field in the problem, and this statement is more than an analogy. It's a genuine statement. The coordinate, part of the coordinate, the diffeomorphism invariance of the original theory descends into the gauge invariance of this new gauge field. Since that diffeomorphism invariance was genuine gauge symmetry of the original theory, gauge invariance will be a genuine gauge symmetry of the new gauge theory. Okay? So just at the level of steric fields, we see that the graviton in the original graviton decomposes into a graviton in the lower dimension, plus a gauge field in the lower dimension, plus one scalar field. The sigma, the scalar field is the size itself. That can fluctuate. Okay? So the field content is this includes this gauge field. So now for the next 10 minutes we're going to focus on the gauge field. Next question we're going to ask is, okay, this is a gauge field, but you see, because nothing else transformed, G didn't transform and sigma didn't transform as we did this gauge transformation. It means that the functions G mu nu and sigma are uncharged under this gauge transformation. So were they charged, they were transformed. Okay? So you could ask, are there any fields in the theory or on some augmentation of the theory that are charged under this gauge transformation? And the answer is yes, as all of you know, but anyway, let me say it, derive it in a clean fashion. Consider a scalar field, or any field, it doesn't matter, but to start with, to be simple, consider a scalar field propagating on this background. Okay? Let's say the scalar field is star. So suppose the action of this field was square root G del M chi del M chi. Okay. And now let me retreat away from my initial assumption that nothing depends on the extra dimension. Okay? Allow the scalar field, and then eventually we have to allow it as well. But to start with, allow the scalar field to have momentum modes in the extra dimensions. take chi and say that sum over m chi m e to the power 2 pi I xd by r. Right, are the most general Fourier. Okay. Now, with this decomposition, what I want to do, okay, is to compute the effective action for chi in the lower direction. So this chi m now is a function of x. Okay? It's clear from momentum conservation that chi m will couple chi m dagger. So this whole action here will have terms which sum over m and m dagger.
What was the period of XD?
It was r. Oh, sorry. Yeah, x was r. It was 2 pi, so no false. No 2 pi. And there's an n. Okay. Now, so what we're going to get is some action that looks like integral square root g times some function of chi m. There'll be a chi m and chi minus m. Now we want to compute what this action looks like. Okay? The goal is clear, right? So in order to do that, you see, the important thing to keep track of is that this thing here has a contraction of this higher dimensional metric. So let's write this down explicitly. So this is square root g dm chi dn chi gm. And gmn for this general metric here is now diagonal between xd and x min. Okay, even supposing that this thing was diagonal, or whatever it was, nothing is not diagonal. Okay, so in order to understand what that action becomes for the chi m, we have to understand what square root g becomes. Okay, and what big G becomes. Okay, so first let's do this in a toy example. Let's imagine that we had a tender in only one direction, because it's enough, because by symmetry we get it. Okay, so what does the metric big G become in that case? Okay, so big G in that case looks like so e to the power 2 sigma, that's the d, this d squared term. Then e to the power 2 sigma times a mu, that one direction, let's say a1, e to the power 2 sigma times a1, and then whatever it was here. Let's say that was eta in that direction. Let's say it was 1. I'll work out this toy example, we'll immediately see the generalization. Okay. Well, this 1 was wrong, sorry. Because this 1 plus 2 sigma times a mu squared. Okay? Now first thing, what's the square root of the metric? Well, the square root of the metric has terms with e to the 4 sigma times a1 squared, which cancel this. That's another motivation for going with this split. This way of looking at it, the a1 squared disappears from the square root of the metric. The square root of g is simply equal to, so the determinant has e to the power 2 sigma, so that's e to the power sigma, times 1. Okay? It's sort of clear if you think about it that this will be times square root of little g in the most general case. Okay? And what does a big G look like? Well, in order to get big G, we have to divide by the square root of this metric, interchange these, put minus signs here, and then we're done, right? So big G inverse is equal to 1 plus e to the power 2 sigma a1 squared minus e to the power 2 sigma a1 minus e to the power 2 sigma a1 and e to the power 2 sigma. Okay, now we're supposed to take this and divided by the determinant of the metric. No. So this is equal to e to the power minus 2 sigma times that. Okay? So it's equal to e to the power minus 2 sigma plus a1 squared minus a1 minus a1 and 1. Okay? Now it's of course very easy to guess the generalization of this. So if we were in arbitrary dimensions and so on. Okay, what we have is that GDD is equal to e to the power minus 2 sigma plus a mu squared. Where every time we now contract indices, I contract with the lower dimension metric. Okay, GD mu is equal to minus a mu okay, and G alpha beta is this clear? It's just an algebraic exercise. I've inverted a metric of that, the form that we wrote down before. Is this clear? Okay? So now, let me take the original action. Let me work in Euclidean space for simplicity. We have del chi del square root g, then del m chi gmn, and write out the terms. Okay. So what we have, we've got integral e to the power 2 sigma times square root little g times, now there's one term where the m indices are both mu, so that's just d mu chi, d nu chi, g mu. That's just the usual kinetic term in lower dimensions. There's one term where one index on chi is a mu index and the other index is a d index. Okay? This becomes d mu chi with a factor of 2. D mu chi d chi times g mu d, which we've seen as minus 8. Okay? And then there's the last term, in which both of these indices are d. Okay? So we get plus dd chi dd chi times this stuff, which was e to the power minus 2 sigma plus 8. Okay, but this can be written as integral e to the power sigma square root g times, now I define a new derivative. Let me define d mu is equal to del mu plus a mu times del mu. Or minus. Okay? Now, can you see that this term, and this term combined together to give me d mu chi, d mu chi. And what we're left with in addition is plus del d chi with d to the power minus I mean, it's easy to convince yourself the reason that this derivative appeared is that it is the derivative that transforms covariantly under the gauge transformation that became the gauge derivative downstairs. How do you see that? You see, d mu under a change of variables xt goes to xd plus lambda. How does d mu transform? D mu picks up an extra factor of derivative of lambda with respect to mu. Right? You see, it's while xd is the guy that's being changed, in variable changes, in the derivative, downstairs derivative changes, it's x mu that picks up the extra term, the d mu that picks up the extra term. From the chain rule. So what I'm saying is that d mu prime is equal to d mu plus dx d lambda by d what do you think? Yeah, exactly. D mu of lambda times d by dx. I'm using the chain. We got the sign right. Sorry. So okay, let me just work it out. Sorry. Okay, so we have so what? D mu prime is equal to d del x alpha by del x mu prime del d by d alpha. Under the variable change under question, so we need alpha. So we had xd was equal to xd prime minus lambda. So we got the sign now. Okay, you worked it out correctly, right? You get the sign right. I hope I've got everything consistent. Yeah, we had we had an a change with the minus sign, so it cancels. Okay? So the reason that this derivative appeared was that it was the thing that was coordinated there. This is covariant under this gauge transformation. This is clear. Okay. Now, this covariant derivative is the same as the ordinary derivative on fields that don't depend on the xt directions. Okay? And also this new term here is 0 on fields that don't depend on the xt directions. However, if we plug in now the expansion, if we plug in now the expansion that we had above, namely x chi is equal to sum over n, chi n e to the power I xd r, sorry, I xd by r n, you see that this derivative, okay, will behave exactly like the derivative in a charged field, where the role of the charge is played by the derivative in the direction. And so will become d mu will become d mu of chi n is equal to d mu minus I n by r n on chi n. Okay? So the chi n's behave exactly like they are charged fields whose charge in this normalization is n over r. Is this clear? Okay, I'll leave it as an exercise for you to show that under the under a global gauge, under a gauge transformation generated by the change in coordinates, okay, chi n's transform exactly like charge fields. Okay, I'll leave that as an exercise. Is this clear? Okay, very good. Okay, so we found something interesting. We found that if we stay directly in our Kaluza-Klein ansatz, if we stay directly like what Kaluza-Klein ansatz, with nothing dependent on that XT field at all, then at least we're coupling to scalar fields. This gauge field has nothing that it's charged. And nothing's charged under this gauge field. However, when we allow dependencies in this additional direction, things are charged under this gauge field, and the role of charge is played by the momentum in the extra direction. Okay? It's clear that the momentum in the extra direction is conserved, because momentum is always conserved. Okay? That maps to the fact that charge is conserved, is necessarily conserved when coupling to gauge field. It's clear that momentum in the extra direction is quantized. And that tells us that what we've got is a compact U-Born theory. Now, theory where the gauge group is compact rather than large. And actually, though we will not pause to look at it at the moment, there are interesting magnetic monopole solutions of this theory. We'll look at it at some point in this course. So Kaluza-Klein monopoles. Okay, and which obey exactly the round quantization. Okay, which in some sense is an explanation of the compactness. Okay, so that's all I wanted to say about charge fields. Is this clear? Is what we've done today. Okay, so we have interesting new phenomenology when any theory of gravity will be compactified on a circle, more generally on a torus. We get new gauge fields. Momentum in the original in these compact directions is charged to this gauge field. Now, of course, since overall momentum is conserved, you can't separate momentum from the scalar field from momentum in the graviton and so on. It's some clear general grounds that any field, whether scalar or vector or the graviton or that carries momentum in the extra direction, will also be charged under this gauge field. Okay? It's more complicated to work out because it's more complicated to solve the equations of a graviton.
The gauge transformations and diff translations in the x direction.
Exactly. Gauge transformations are translations in the x direction, and it's generated. Exactly. Okay? So, exactly. So, as Roman said, it's sort of clear just from the structure that momentum in the extra direction, abstractly, no matter what carries it, will play the role of charge. Okay, great. Now, what's the next? What's the next thing I want? The next thing I want to do was to understand how. Okay, let's do the graviton. The graviton sequence. The three fields I want to understand. First is an arbitrary scalar field. The second was the graviton, the graviton itself, graviton dilettante system, and the third is the beam field. Okay, so let's try to understand the graviton. Okay, so what we're going to do is now work out the effective Kaluza-Klein reduction for the graviton. Here I'm going to appeal to one. It can be shown that, basically because the algebra is too big. Okay, so the one it can be shown that I'm going to do is that if you take the metric of the form that we have done at the beginning, and you calculate the Ricci scale, that metric, okay, then the answer you get is equal to the Ricci scalar of the lower dimension, G, the small g mu, minus 2 e to the power minus sigma then squared of e to the power sigma. So what is RD if the R, big R is the Ricci scalar in the big theory in all dimensions. RD is the dimensionally reduced. It's the Ricci scalar built out of little g. Okay, let's call this. Let's give it a better name. Let's call this R 26, and let's call this R 25. Just to make it clear. It works more generally in very specific, but just to make it clear. Okay, and minus 1 by 4 e to the power sigma. Alright, while the derivation of this is a straightforward exercise. It's a pain in the neck, as you can imagine. Okay, and we're not going to try to. Well, some things are obvious, right? It's obvious that this expression, which is invariant under all coordinate invariances, should give you something that does not depend on A, but only on F. This thing is two derivatives, so this thing has to be two derivatives, and so on. So all the simple consistency checks will allow you to fix what the form that could have taken up to some coefficients. Okay? And computing the coefficients would be a pain. Okay? But basically the structure sounds very reasonable and one can verify it, apparently, to say I've never done it, and by direct calculation. Okay. Fine. Assuming this, now let's go. Okay. So let's start with the action, which was square root g. Now this is the big G, remember, times R26 times, let's put it in the term, e to the power minus 2. Okay? And plug in this expression. So firstly, what does square root g become? Square root g, if you remember, became integral square root little g times e to the power sigma. Okay? Then this R26 we just got, it's R25 minus 2 e to the power minus sigma times del squared e to the power minus sigma. Okay? And then we have minus e to the power 2 sigma by 4. FPD, of course, you understand, right? It's the gauge field builder field. That is. Everything has a minus 2 phi. Thank you. E to the power 2 phi minus 2 phi plus 2. Okay. Now, in order to process this equation, we notice that this term here. Let's focus on this term. This term here is an integral square root g e to the power minus 2 phi. Now the plus sigma cancels this minus sigma. We get minus 2 and del squared of e to the power. It's more usual when we got a scalar field to write the kinetic term as del sigma del sigma. Okay? So in order to do that, let's integrate this guy by parts. Integrating by parts gives us an additional minus sign. And then the derivative is transferred to the just derivative of this guy. Okay? So this becomes plus 4 e to the power square root g del mu e to the power minus 2. Sorry, plus 2. Del mu e to the power minus 2 phi times del mu e to the power minus e to the power minus sigma. Okay? And now we act these del mu's. So we get minus 4 integral square root g del mu phi del mu sigma e to the power minus 2 phi minus. Let's have a sign. Sorry, this one was a plus. That's right. And now I've got the sign minus. Yeah, this was plus. Clear? Okay? So the whole action can then be written as integral square root g e to the power minus 2 phi plus sigma into, there's R25, then there's minus 4 del mu phi del mu sigma, and then there's a plus e to the power 2 sigma by 4 f. Now it's conventional when you're dealing with gravity theory to call whatever comes outside the R e to the power minus twice the delta. 25 is equal to phi, which is 26 dimensional dilaton, minus sigma by 2. Oh, I'm sorry, what I've forgotten in all of this is that we should have started with the kinetic term for the dilaton as well. Sorry. So there was a plus 4 d mu phi, the whole thing squared, which was in this action. And that's carried through everywhere. The original higher dimensional theory had a kinetic term for the dilaton.
So that's mu.
Yes, it's mu because we assume that the dilaton does not depend on the original dimensions. Yeah, had it depended on the original dimensions, we would have to do the same exercise that we did previously.
Yeah,
With this,
it will be charged and
it will be charged. So let's ignore that effect. We've already dealt with it. Okay, let's just. Okay, good. So now what we find, you see, there are these terms. Suppose we rewrite everything in terms of this guy and sigma. This term and this term combine to give you d mu of phi minus sigma by 2 into d mu of phi minus sigma by 2 with a plus 4. Except that the term that was, except that we need to add to this minus d mu of sigma the whole thing squared. Okay, so I'm telling you that these kinetic terms, the scalars, are equal to that. Okay, which is then equal to 4 times d mu of phi 25, d mu phi 25, and then minus d mu sigma. Okay. Okay, so what's the net effect? So what's the final answer? The final answer is that we've got integral square root g times r, now everything is lower dimension. Okay? Times e to the power minus 2 phi. Okay, maybe I should write 25 times, times, again, e to the power minus 2 phi 25 times r 25 plus d mu phi 25 the whole thing squared with a 4 minus d mu sigma the whole thing squared. Okay, and then minus e to the power 2 sigma f measure. That's a final answer. Okay? So you see, apart from these two terms, it's exactly at the same form of the action we started with. We started with an action which had R26 plus 4 times d mu of 526 the whole thing squared, and we got the thing of the same times e to the power minus 526, and we got something exactly the same form. Okay? Except that now we've got additional terms. The additional terms are the scalar that represents the size of the circle, okay, and the kinetic term for the gauge field. fields in the problem are this low dimensional dilettone and the kinetic at this sigma. Okay. Now there's something that here might be worrying you. It might be worried that these two kinetic terms are opposite sign. So you might think that one of them therefore is the wrong sign kinetic term. But that's not true, because remember that this guy is multiplied by the e to the power minus 525. So when you find the equation of motion of this 525, you get an additional term from integrating by parts here. And both of them obey ordinary sign, effectively ordinary sign kinetic terms. Let me say that again. If you define a new field, let's say e to the power minus, if you want to find a new field such that this thing is not there behind its kinetic term, you would say that zeta, say, is equal to e to the power minus phi. Then this will be proportional to del mu zeta. Okay? But you get the right side kinetic term when you work that out. Okay, so sorry, I said that wrong. Sorry, I said that wrong. Basically what you want to do is to define canonical fields for everything. So suppose you went to Einstein, suppose you went to Einstein. Okay? Suppose you define a new metric such that the Ricci scalar for that new metric didn't have an e to the power minus 525 in front of it. So that's some conformal transformation of the survey. Okay? Then the kinetic term for the graviton is just standard, and the kinetic term for the dilettone will also be standard. Okay? But you see that new Ricci scalar, the rescaled Ricci scalar has extra contributions proportional to del squared of phi, which when combined with this term gives you the correct sign. Sorry for the wrong statement. But so the net point is that because of this e to the power minus 525, every field has the right sign. Though it's not manifest. It's not manifest in this way. Okay? Another way to say it is that this problem of the wrong sign kinetic term existed also in the parent theory. So whatever solves it in that parent theory also solves it in the current theory. It's no new issue. Okay? Good. So that's all I wanted to say about this graviton dilettone sector. Okay? The effective fields are a d minus 1 dimensional dilettone, d minus 1 dimensional metric, scalar field for the size of the circle, and the gauge field. And you see what kinetic terms look like. Now the scalar field could easily be given charge for circle base. And you can play with the motion games. Okay? The last thing to say is that because this form is exactly the same as the parent form we started with, if you now dimensionally reduce further, you can do that recursively. Okay? So if you dimensionally reduce down p dimensions, the new d-dimensional dilettone, the new effective dilettone, will be the old one minus sigma 1 by 2, minus sigma 2 by 2, minus sigma 3 by 2 all the way. Okay? And you'll have many new scalar fields, sigma 1, sigma 2, sigma 3, which are like this. Okay. The last dimension, the last thing that I wanted to work out was this B field. In view of time, I'm going to delete this for you as an exercise. Okay? So, well, let me sketch the answer and leave the working out of the details for you as an exercise. Okay. So, suppose we have this B mu. Okay? Now, B mu, let's say we start with B and N. Now there are two options. The Mn in B could be either D, height 26, or it could be mu. Since the field is antisymmetric, you can't have two of them in D. Okay? So there are two options. There's either B mu D or there's B mu. Okay? This let's call A mu prime. Okay? This now behaves like an honest gauge field in one lower range. How do we see that? The gauge symmetry of B was B prime is equal to B plus D of lambda mu, where lambda is any one form. Now an arbitrary one form, D of lambda where lambda is any one form. Now an arbitrary one form is lambda is equal to exactly some chi times dxd, okay, plus chi times dxt plus b mu times dx mu. An arbitrary one form. Let's take d of that and assume, as we've been doing, nothing depends on. Well, actually, for the statement we don't even need to assume that. So let's say d of that. Okay, there will be a term here proportional to d chi wedge dxd. Since it's antisymmetric in d chi, we don't need the derivative in the d direction. So that will be d mu chi times dx mu wedge dxd. Okay, so the change in b mu d is exactly like the change of a mu under the gauge transformation generated by the gauge parameter chi. This is shift by d mu chi. Okay, so the gauge symmetry, you see this gauge symmetry was gauge symmetry under a 26 parameter group. Because there's lambda, there's one form, components 1 to 26. 25 of these 26 parameter groups just generate gauge transformations of this period, of this period. The 26 guy generates not a one form gauge invariance, but an ordinary function gauge invariance for the effective ordinary gauge field in U prime. Is this clear? So under Kaluza-Klein reduction, the B mu nu field in 26 dimensions gives rise to a B mu field in 25 dimensions plus an A mu field, an ordinary gauge field. Okay, now the exercise I want to leave for you is to work out what happens to the original kinetic term of the theory was square root g h mu nu lambda h mu nu lambda. This was kinetic term in higher dimensions. I want you to, as an exercise, to work out the kinetic term in lower dimensions. The dimensionally reduced kinetic term. We'll briefly, so please try to do that in next class. We'll briefly discuss the answer next class, and then next class we'll move on actually considering string theory rather than field theory with the right compatibility. Okay, something I should say about this free field is that, so we've got a new gauge field here, and you might wonder what is charged under this gauge field. Now we've already seen last time, we've already seen this lecture, the momentum around this circle is effective charge under the gauge field that came from the graph. So don't see bit too much of that also gave us the gauge field that came around, that came from this B mu field, and it's not true. You take a mode that has momentum around the circle, there's no sense